Hi, my name is Spoorthy Paresh, and I'd like to present my work titled Representational Learning Assisted Matrix Factorization Framework for Electrical Load Disaggregation. In the electricity generation, transmission, and distribution scenario, it is important to be able to manage energy consumption at the demand side for efficient supply-demand chain. And at the utilities level, it therefore becomes imperative to know peak load consuming durations during the day and to be able to mitigate them using varied incentives like the demand response. You must also be able to plan their operations based on consumption forecasts for a region, locality, or for a set of households. At the consumer end, energy management is possible when they have an understanding and awareness of where their energy is actually getting spent. If the appliance health is equally important in order to be able to optimize energy consumption in the household. And all of this help in reducing the electricity bills of the consumers and improve energy consumption management. To this effect, smart meter data analytics provides a bucket of algorithms which provide analyses at the level of the retailer, aggregator, and consumer, and allow them to work together for demand-side energy management. Of particular interest is the load disaggregation process, which refers to the process of obtaining disaggregated appliance consumption from aggregate smart meter data collected from households or commercial complexes through electrical smart meters. This data is relayed to the utilities, which analyze the data and give the disaggregated results to the consumers. The disaggregated results consist of the appliances identification given the smart meter data and also their consumption estimates. This helps the consumers in knowing where their energy is getting spent. It also helps the utilities to recommend appliance usage methods to the consumer, and together they could work towards supply-demand regulation. Load disaggregation frameworks are different for different smart meter granularities. Smart meter data is collected at high sample rate, that is 1 megahertz to 1 kilohertz, and at low sample rates, that is 1 sample in a minute to 1 sample in 5 minutes, and to very low sampling rates, that is 1 sample in 15 minutes to 1 sample in 1 hour. Of interest to our work is the low sample rate category, where we have vague information about the appliance operation on the aggregate smart meter data waveform. And the on-off instances are not available, nor do we have information about the state switching within an appliance. And therefore, modeling and optimization techniques are necessary to be able to disaggregate this category of smart meter data. Load disaggregation is challenging because of the multiple appliances that are usually operational at the same time in a house. Along with this is the fact that different households have different frequencies at which appliances are operated. The geographical context also add another layer of complexity to the load disaggregation frameworks. The appliances that are used also change from region to region, and all of these factors have to be incorporated into the load disaggregation formulation for efficient disaggregation. In the low sample smart meter data category, traditionally neural network based, machine learning based, or dictionary learning based models have been used to learn the interdependence between the aggregate smart meter and the different historical appliance information. And the models that are learned thereof, one for each appliance of interest, are used to disaggregate any new incoming smart meter data. As we see, the amount of training data that is needed to disaggregate smart meter data using these frameworks is quite humongous, and this leads to computationally intensive algorithms. In order to simplify the load disaggregation frameworks, a new thread of research is emerging, which is called the semi-supervised learning approach. To the right, we find the sample block diagram of how semi-supervised learning approaches work. On one end of the neural network architecture, we have the aggregate smart meter data fed in. The representations are learned at the hidden layer, and along with the regular visible layer of the neural network, there is another layer, visible layer, that's appended, which we call the appliance model matrix. This appliance model matrix consists of the historical information that's needed to disaggregate the smart meter data. Now, this appliance model matrix is connected to the hidden layer of the neural network architecture. The representations from the hidden layer are mapped on to this appliance model matrix, and the mapping is learned using iterative minimization algorithms. Now, as we see, we are learning one mapping, M, as opposed to multiple models. And this definitely reduces the amount of complexity that's involved in load disaggregation frameworks. The appliance model matrix can consist of information such as the typical on-off instances of each appliance, which can be then used to identify the existence of an appliance in the smart meter data. However, appliance reconstruction is also an important aspect of load disaggregation because it helps with consumption estimates for each appliance. And across a timeline, the consumer will be able to know how much energy has been spent for each appliance. It also helps to facilitate appliance health monitoring. And this is very important because when the appliance health degrades, then there is more energy that's spent than that is required. So taking this into consideration, we propose a representational learning assisted matrix factorization framework, which consists of a generative neural network. And on one end is the input smart meter data. And on the other end, connected to the hidden layer, is the historical information about each appliance, which is collected in the form of appliance signature matrix. And the generative neural network learns the representations of the input smart meter data in an unsupervised fashion and maps this to the appliance signature matrices on the other side of the hidden layer. The mapping consists of information about which appliance consumption behavior corresponds to the input smart meter data. In this work, we have used Restricted Boltzmann Machine because we know they are good approximators to the input data, and they are very efficient in learning latent representations. In electricity load disaggregation, latent representations refer to the learning of the magnitude, typical magnitudes of energy consumption, the typical durations of each instant. And once such factors are learned, when they're mapped onto multiple of the matrices, appliance signature matrices, the combination of the consumption behaviors to which these representations conform will be the disaggregated estimates. Because we are learning the mapping in a regressive fashion, along with the identification, the appliance reconstruction is also enabled. We implement this framework in the following way. The appliance signature matrix L is related to the data representations H through a matrix factorization framework. The mapping between the representations of any arbitrary smart meter data and the appliance signature matrix is learned through the least squares function. And once the mapping is learned, the disaggregation is achieved through the dot product of the mapping function M and the data representations. The disaggregated estimates consist of appliance reconstruction wherever an appliance is estimated to be contributing to the input smart meter data. And when there is an appliance which is not contributing to the input smart meter data, there is no reconstruction. We implement this framework on different data sets to check for its applicability across geographical contexts. And we also use the most commonly used appliances within that particular data set to see if it is generalizable across appliances as well. The results show that from low power consuming appliances such as the refrigerator to high power consuming appliances such as the washer dryer, we have near perfect reconstructions. When we calculated the RMS of percentage of error energy correctly assigned, which evaluates the reconstruction error, we found very low values across the different appliances and for different data sets, which shows that the framework is generalizable across geographical contexts as well. In summary, we present a computationally simple and reliable framework for load disaggregation using a two-stage learning approach. And we present a demonstration of this framework using appliance signatures for disaggregation. And this enables appliance reconstruction along with appliance identification. We've also observed that this framework is applicable across geographical contexts and for different data sets and for different appliances of consideration. Thank you. I'm open to questions now.